Great. So welcome, Summayah and Luke. Thanks for joining with this session for solving an exercise from the mini school on elementary introduction to category theory. This exercise grew out from a question that was asked by Professor Josef Honerkamp. And here we have also a slide that he kindly sent us by email, which illustrates what he was telling us at the lecture of the mini school. So where should we start, Summayah?
Can we start with just in terms of how the functor is defined and what exactly gets mapped to what?
Yeah, that's a very good suggestion. So this exercise talks about a certain functor, and I think the aim of the exercise is to show that that thing is a functor, right?
Yes.
But maybe even before we start describing the functor, we should first maybe describe what the category is, right?
Yeah.
So I would like to suggest that we do not take a fully rigorous approach with this in the sense of writing all sorts of mathematical formulas. Rather, let's apply rigor as much as needed in terms of understanding fully what's going on. But if we feel we understand, we don't have to go in further detail. Are you happy with that?
Yes.
Okay, great. So let's think of this in terms of two areas, the left-hand side area and the right-hand side area that I'm drawing here. Do you see right on the right of the picture?
Yes, Prof.
And the left-hand side will be our category, and the right-hand side will be the category inside which we are mapping the first category. So this right-hand side category actually will end up being the category of vector spaces. And let's assume that we are working with vector spaces over real numbers, shall we?
Okay.
So that's the category that we described at the lecture in the mini school. Now the left-hand side category will be created out of a specific vector space. And just to illustrate this on an example, shall we work with simply r squared?
Yes, I think that's what the question also refers to when referring to the objects being points in space. Well,
That's
that was my
right.
understanding.
Yeah. It could have been any vector space, but let's limit
Yes.
ourselves on the specific example so we can get a better grasp of what's going on, being more concrete.
Should the subscript at the vector, the category of vector spaces also then be vector spaces over R2, or
So
is vector spaces over R2 are real vector spaces, so that subscript is sufficient?
there is not really a notion of vector space over R2 because what we put there as a subscript will be the field over which we are taking our vector. R2 is not a field. I mean, it can be turned into a field by thinking of it as complex field, but we are not considering vector space over complex field. We're considering vector space over the field of real numbers.
Okay.
So that subscript there is fine.
Okay.
So that field is the place where your scalars come from. So our scalars will still be real numbers. Okay. Now we want to turn this r squared into a category. And to do that, we'll have to say what its objects are and what the arrows are, right?
Yes.
So the objects of this r squared category will be just points in r squared.
Yes.
So let's pick 3 random points, maybe with coordinates 1, 1. Not worrying too much about the geometry of the placement of these points. Let's call this 1, 2, and well, actually, maybe we should worry about the geometry. It's nicer if we do. So let this be 1, 1, and let that one be 1, 2. So such points are objects of the left-hand side category. And for every 2 objects, there will always be exactly 1 arrow connecting them. And the way we will think of this arrow is like the usual vector in physics or in applied mathematics. So it's an arrow going out from one point to the other. There are always arrows in both directions, right? But we just pick one for now.
Yes.
So in a setup like this, composition is kind of obviously defined, because like if you have an arrow going this way, yeah, and you have an arrow going that way, then there is a unique arrow connecting this the first point and the last point, and that unique arrow will be your composition of the 2 arrows.
Yeah.
So is it clear how composition is defined?
Yes.
Yes.
Okay. What's the next step? Is it
The
clear? Is it
second-
yeah? Sorry.
Oh, sorry. I thought we were done defining this first category.
Well, we kind of defined the directed graph, but we remember a category is a directed graph together with composition, which we also defined. But now we need to check that the composition is associative.
Yes.
And that that the identity law also holds, that the special arrows composed with other arrows give back other arrows. So do you think it's obvious why it's associative?
Yes.
Yes, I think so too.
It's kind of because there is always exactly 1 arrow to be the value of your composition, right?
Yeah. So whether you combine the first 2 as 1 arrow or the last 2 as 1 arrow,
Yeah.
and then combine them all together, you always end up with that 1 big arrow.
Yeah. And the same goes for identity arrow. I mean, the identity arrow would be something, I guess, we don't even draw.
Yeah.
So that's the special arrows we talked about at the lectures for the mini school. And so for the same reason, if I have something here that's kind of almost like a 0 vector, right? And I combine it with something else, then it gives back that longer arrow and also on the other side, you know?
Yeah.
Yeah.
Because there is always exactly 1 arrow. So as a category, this left-hand side category is something quite simple and obvious. The non-obvious part will be the functor. Of course, in R squared, the way we usually think of R squared as a vector space, we kind of have this coordinate axis, right? And then in usual mathematical way of thinking of R squared, we think of the points of R squared as arrows connecting the origin of that axis with that point.
Yes.
But that's not how we want to think of arrows here, because we have arrows between any 2 points, not just the one with the where one of them is the origin, right?
Yeah.
And on the side of physics, at least this picture that Professor Honerkamp sent us, there is terminology to distinguish between these 2 kinds of arrows. You see, the position vectors here and the free vectors. So I actually didn't know about that terminology. So we don't really care about position vectors in terms of the left-hand side category. In fact, in the left-hand side category, we've even kind of almost like forgotten what the origin was.
Yes.
And now, what we want from the functor is to name the origin. So, yeah.
Sorry. Before we do the functor, can we look at the second category?
Yeah, that's a good idea. Yeah. So the second category is the one we already described before, a bit briefly maybe. So let's expand slightly on that. So the objects in the second category are individual vector spaces. For example, one of the objects could be the vector space R squared, and another object could be the vector space R cube.
Yes.
Okay.
An morphism from one vector space to another, an arrow from one vector space to another, would be
Space homomorphism.
yes, which is also called a linear map or a linear transformation. So just to illustrate on a picture, if we think of R squared as something drawn with 2 coordinate axes and R cubed with 3, then we could consider insertion of this plane, let's say if these are x, y, and z coordinates, into the yz plane. And that insertion will define a linear map, which maps every point xy to a point 0 xy, because the x coordinate of the other space we always keep to be 0, so we end up with the actual yz plane. Does that make sense?
Yes.
Mm-hmm.
And it's not difficult to check that this map will be a linear map, because it will preserve addition, scalar multiplication, since both of these operations are kind of defined on how things act in each coordinate, and the things that happen to each coordinate don't really change. Here they're the same. And the preservation of the 0 vector, which is also very important, is ensured by the fact that this thing itself is a 0 vector. I mean, it's in the number 0. So if we try, for example, to first add 2 vectors on this side, which is going to give us this, and then map, if we map them afterwards, then we will have a vector 0, x1 plus x2, y1 plus y2, right?
Yep.
But if we did this the other way around, and I think I've moved away from the visible part of my visible in terms of the camera that I'm recording, so let me shift it slightly, which you wouldn't notice because you only see you don't see my movement on the screen, and I don't see your movement, so sometimes we might get lost in the sense of finding each other on the board. So if I first add vectors and then map them, so this vector would map here, right? Now the question is that the same as first mapping them and then adding them? And if we first map them, we would get something like this, right? So that would map here, and the other one would map here. And then if we add them after mapping, because 0 plus 0 is still 0, then we'll be fine. We will still get the same result.
Yes.
And one can write down similar proof of preservation of scalar multiplication.
Yes.
Okay, so and then the fact that composition is defined, that comes from, I mean, the composition is defined using composition of linear maps as functions, but that the fact that composite of 2 linear maps is still a linear map, it's also something that's standard and easy to prove as well. If one hasn't proved it before, one can also try it by oneself. So we get this right-hand side. Do you think that I've done justice to your request, Summayah? Do you think we have a good understanding of the right-hand side category now?
Yes.
Mm-hmm. Okay, so now let's see how we're going to establish a functor between the two, and for that purpose we're going to, the values of this functor on objects will always be R squared. So that's one thing to remark. So all the objects will always map to R squared.
So, do they map to different R squared vector spaces?
Yes.
Actually, I'm wrong. I'm wrong in what I said. Your question made me realize I'm wrong. So, remember, a vector space consists of a data of the set, addition of vectors, including the 0 vector, and scalar multiplication, right? So we're going to be changing all the time. So we're going to be keeping the same underlying set r squared as v. So v will always be r squared, but we're going to be changing this all the time.
Yes.
Depending on 1, 2. I mean the starting vector. So if the starting vector, sorry, I shouldn't call it starting vector, I should call it rather starting point, right? So let's do the general case. If the starting point is point xy, do you think it's better to do a general point xy, or should we stick to some specific values of x and y, like 1 and 2?
I think we can go for the general point xy.
Yeah.
Okay. So that will be mapped to a vector space where we can maybe call this data something, so we can then refer to it. So plus xy, 0 xy, and dot xy, where dot will be scalar multiplication for that. And so intuitively, if we go back to the slide of Professor Honerkamp, we see here kind of what's supposed to happen. So the xy on this picture is this point here. Actually, no, not this point, sorry. Well, yeah, it actually is this point. And this point, as suggested by this picture, this point is supposed to become the origin of the coordinate axis. So that means that on our side, it means that we want 0 xy to
Sorry.
Yeah, what happened?
In reference to what was just said, in terms of the origin being the xy being this point, and then mapping to the origin. This is the origin. So how is it our xy point when our xy that we said just now that it kind of we alleviate the origin and we just work with x and y.
Yeah, that's why on this picture on the left hand side of that slide, you've got two coordinate axes, the top one and the bottom one. And by the way, the label xy of those axes has nothing to do with our xy.
Yes. So essentially what happens is, so does the origin of the one get mapped to the origin of the other?
Yeah, so before we describe, I mean, so the two are there to show us where the arrows will get mapped to. But before describing where arrows map to, let's first describe where points map to, where objects of the category map to. And then after that, we will describe where arrows map to. So arrows will map to linear maps, which will be kind of translating along that capital Y vector here.
Okay, then we can do the points first. Maybe it will make more sense.
So we want to we actually want here, instead of v, we want r squared, the genuine r squared. And but we're not going to think of r squared in the usual way. We're going to change its 0 vector. We're going to change its addition. We're going to change its scalar multiplication. So the new 0 vector of r squared would be declared to be the point xy we started with. And now if I have my point xy, right, and I have two other vectors, let's say x1, y1 and x2, y2. I now have to describe how I add them, right? So what is going to be x1, y1 plus and that addition is according to the point xy, x2, y2. What is that going to be? Now I can easily explain on the picture what it's supposed to be. I'm going to connect these two with the vectors, and then I'm going to use the parallelogram rule. So that point there is going to be the value I'm looking for.
Yes.
So you see how it really depends on what this xy point is, because if I had a different point of reference, right, then my parallelogram would have given me a different value. Yeah?
Okay. Okay, this is making more sense.
So basically what this point is doing is that it is kind of telling us how we think of other points as vectors. Remember, there is usual coordinate axis for r squared, right, given by origin being 0, 0. And that allows us to think every point as a vector starting out from that origin. But
now we're making the origin
that's
the
right, yeah.
point that we are mapping.
Exactly, yeah.
So every vector space in vec R, like the R2 that we are mapping to, has a different origin point.
Yeah,
depending
exactly,
on what-
yeah.
Yes.
Yeah.
The origin point always being the,
Yeah.
the object that we started from in our first category.
Now, yeah?
Now this addition, how exactly is it defined?
So on the geometrically, it's defined the way that we're describing here, but we can also find its algebraic definition by realizing that if I go back to my usual coordinate system, I actually don't really need the axis. I just need to know what the origin is. Then if I draw in these vectors here, then I will notice that xy plus that vector I'm looking for. So let's call this vector something. Let's call this vector p and the other one q. So xy plus p, right, is going to give me x1, y1. Do you agree with that?
Yes.
Yes.
And so then p ends up being xy minus x1, y1.
Yes.
Now, as a vector, if I subtract these, I will get something that has the same magnitude and direction as p, but it will be positioned at the zero origin. So I will actually, the difference of these two will actually give me something that goes like this.
Yes.
So I will have to shift it back to where I want later on. So by taking this difference, and also by taking a similar difference for q, so by taking actually I made a mistake, right? The difference should be the other way around. Yes.
Yes.
Thanks. Yeah. So it's x1, y1 minus xy. So that's p, but that's p kind of shifted away, right? And then
x2, y2 minus xy would be q.
That's right, yeah. That's q. And then I want to add those vectors, right? I want to add the p and the q. So q will be somewhere here. I'm going to add them. Yeah?
Yeah.
Okay.
And then I'm going to take the sum and shift it back, so that shift it back to that position, which is adding back this vector.
Yeah.
Yes.
So when I add them, I will see that in the formula I will have x1, y1 plus x2, y2, and then minus 2 times, oops, I moved something else here, sorry. Minus 2 times xy, yeah?
Yeah. And
so that's
then
my p plus q, but it's actually not really p plus q genuinely. It's the one that hasn't been shifted
moved
yet.
back to the origin. Yeah.
And when moving back to origin means adding one more copy of xy, and then it will, because it's minus 2 of them, and I will add 1, I will eventually get just minus 1 of them, right?
Yeah.
So then the final result can be written with a formula that's quite elegant, and that looks like this. So it's x1, y1 minus xy. So I've put that in the middle, just like this appears in the middle here. And then plus x2, y2. You see?
Is this normal addition of vectors in R2, or is it our addition using xy?
So this is not the normal addition, because the normal addition is when this is 0 vector, when this is 0, 0. So it is going to be the addition in this vector space where we assign xy to. But remember that xy is fixed here.
Yes.
So it's actually still a binary operation because xy is fixed. And what this tells us, of course, it identifies the coordinates of this point. So if I expand it further, I'm going to get xy minus x plus x2. Sorry, x1 minus x plus x2, and the other one will be y1 minus y plus y2. And these two numbers are, of course, the coordinates of this point here. The actual coordinates, and that's what we want, because we are representing points as in terms of their actual coordinates. So we need to know what their actual coordinates are to define addition in R squared, to define a new addition in R squared. So we've now defined the 0 vector, the new 0 vector, and the new addition, right?
And we still need the new multiplication.
And we still need a new multiplication, yeah. So for the new multiplication, once again, I have this fixed vector x1, and if I have another vector called x1, sorry, I meant to say xy, and if I have another vector called x1, y1, then I want to connect them up like this, then stretch it by a factor, right? Let's say I'm multiplying by k. Stretch it by a factor, I should get the thing that I want to be k times that, for a real number k, for a scalar k. So once again, I will have to first, so let's define this thing. So k times, according to point xy, k times x1, y1 is then given by, so let's work this out. So this vector p is the same as before. That's x1, y1 minus xy, yeah? So by considering this difference, we actually end up with p being shifted to the origin 0, 0, right?
Yep.
Then we multiply that by scalar.
And then we shift it back.
Yeah. So we multiply that by k, and then we add to that xy. So the result of that will be k times x1, y1 plus k minus 1 times xy, right? And you see how with some very kind of easy geometric pictures and intuition, we are arriving to something that computationally is starting to look at quite ridiculously complex, especially if we if we would want to, after this, to check all the axioms of a vector space are true.
Prof, isn't it k minus k minus 1?
It's 1 minus k, isn't it? Yeah, that's what you mean, yeah? Because k is with minus sign, and then we have plus 1. So it's 1 minus k here, not k minus 1.
Yeah.
Yeah, you're right. Yeah, thanks. Okay, so we will have that thing here, whatever we wrote here. That will be exactly the coordinates of this vector p being stretched by some k factor. So is it fine for both of you?
Yes.
Yes.
Plus 1 minus k xy. And that, of course, can be expanded to equal to the vector whose first coordinate is kx1 plus 1 minus kx, and the second coordinate is ky1 plus 1 minus ky. So we've got all the three ingredients now. We know what the zero vector is, we know what the addition is, we know what scalar multiplication is, but we don't know that they obey all the usual vector space axioms, right? And that's something that I suggest we don't do, because we're going to run out of time if we start doing that. There are quite a lot of axioms for a vector space. Intuitively, it kind of should work out, because think about it. All we're actually doing is declaring a new origin, and then the geometry kind of tells us the parallelogram geometry and the multiplication of a vector by a scalar being stretching, kind of that intuition tells us that everything should work out, right?
Yes.
Because it's just a shifting of the vector space.
Sorry, what did you say, Summayah?
Isn't it just like a shifting of the vector space?
Yeah, it kind of, yeah, exactly. Yeah, exactly, yeah. So, okay, so one would have to prove that these things are vector spaces, and after that, then the next step is to describe how we map the arrows, right? So going back to our example for 1, 2, and 1, 1, 1, 2 would map to a vector space where the plus is according to 1, 2, right? And the 0 is according to 1, 2. And the scalar multiplication is according to 1, 2, just like in the general case, yeah? And 1, 1 would map the same way, plus being according to 1, 1, and 0 being according to 1, 1, and scalar multiplication being according to 1, 1 again. But now we have to describe where this arrow will map to. So again, let's draw a picture for that. I'm going to move up for the picture. So imagining that we have 1, 2, and we have 1, 1. A point in the first vector space, by first I mean the one where 1, 2 was mapped to. So let's call this thing f of 1, 2, because if f is the name of our functor, then we can call this entire vector space f of 1, 2, and the other one f of 1, 1.
Yeah.
So an element of f of 1, we have to describe a linear map from f of 1, 2 to f of 1, 1, right?
Yes.
Now, if I take an element of element t, let's say, of f of 1, 2, how does it look like? Well, it's just a point in the same r squared, right? So let's say that point has its original coordinates being t1 and t2.
Yeah.
We now have to map that linearly to another point in the same place, but now seen as a point of the other vector space, right? So
Yes.
some t prime. And this transformation is to be linear, so 0 vector must map to 0 vector, and that means that this thing, which is a 0 vector in f of 1, 2, must map to that, which is a 0 vector in the other one, right?
Yes.
So we are kind of forced to map this thing to that. We don't have a choice for that, huh?
Yeah.
But now, according to how we mapped that, we want to map other things in such a way that structure is preserved. And then the obvious intuition here is that maybe we should simply translate everything according to this free vector here.
Yes.
So if I have if I think of this as in terms of that vector, then translating means again applying the parallelogram rule, right?
So it'll be T1 and T2 minus 1.
So let's work it out what it will be, yeah. We already have a formula for that, right? You're right, yeah. So it will be T1, T2. In fact, it will be whatever would have been that according to 1, 2 with 1, 1, yeah? Didn't we work out in general that parallelogram rules gives that result exactly?
Where?
Right here.
Yes. And
So,
then minus.
Going back to this picture, Summayah.
Yes.
Remember,
but I'm using class of 1, 2.
because in this picture, that thing was this kind of the source of the parallelogram.
Yes.
And that on our algebraic side was represented by xy.
Yes.
Now here, the source of the parallelogram is this. So that's our xy.
Oh, okay.
So we've now described the mapping. We've described a way to map things. So we say that T1, T2 must map to whatever the result of that computation is. So T1, comma T2 plus 1, 2 plus 1, 1, which we know what it equals to because we have that kind of relative plus defined for all the cases, yeah?
Yes.
We would have to check that this is a functor, well, first of all, we would have to check that this is a linear map, yeah? And again, we are not going to do it right now. We're not going to do that calculation right now. Let's just believe it will be for now, but one has to check that. And then we would have to also check that this does give a functor, the axioms of a functor itself. And I think showing that composition is preserved by the functor will be very easy to see geometrically. So let's illustrate that geometrically. So imagine you've got your distinguished point, which identifies for you the vector space to which this point is mapped to, of course. Yeah. So if this is point P, this will be f of that point. Yeah.
Yeah.
The vector space. There is another one called Q. We'll have f of Q, and then there is another one called R. This will be f of R. Yeah.
Mm-hmm.
And the unique arrow here will give rise to a function here, and the unique arrow there will give rise to a function here. But there is also a arrow all the way across from P to R, right?
Yes.
And that will give rise to another function, and we want to check that this other function will be the composite of the other two.
Yeah.
So now how does the first function from f of P to f of Q work? If I take some point, then to map it by the first function is to take the result of this parallelogram, right?
Yeah.
So if this is the f of the arrow PQ, and if this is the f of the arrow QR, so let me write it like this to represent the arrow, and then this is the arrow f of the arrow of PR, and if this is the element T from f of P, then this will be the value of the linear map FPQ on the element T, yeah?
Okay.
Which will be f of Q. Does that make sense?
Yes.
On the other hand, if I now map this further by the other map, the f of QR map, then it's again a parallelogram, right?
It's going to be a similar situation.
So mapping this further means applying f of QR to the result of the previous mapping, which was f of PQ of T. Yeah? and that will be an element of f of r. Okay, so we've now kind of looked at trajectory of what happens to the point, an element of f of p, which is mapped up by the first arrow and then the other one. But now let's see what happens when we map it all the way across by f of pr. That means, and I would want to probably change color now, that means taking a parallelogram composed of these two arrows, right?
Yes.
And of course, geometry tells us that it will be exactly this parallelogram.
Yeah.
So that should have been the value of f of pr applied to the vector, the point t, and now we know that there must be equal by the geometry.
Yes.
So it gives a nice illustration of preservation of composition by the functor in terms of geometry of parallelograms.
I just have a question.
Yeah?
You know that the arrows in our R2 category are unique, right?
Mm-hmm.
Wouldn't that mean that in the vec R that the arrows would also be unique?
The ones that come from the left-hand side category by the functor, yes.
Okay, because then if they are unique and there does exist a composition from B to R.
No, but the vec R has many other arrows, but they never get used by the functor.
Oh, true.
Yeah. And we want to, so out of that chaos of arrows in vec R, we're kind of carefully identifying these arrows, and we want to, by the functor f, and we want to make sure that these identifications kind of match with each other in terms of composition.
Okay, that makes sense.
Of course, a similar diagram can be drawn for preservation of identity arrows, because, I mean, identity arrows are just zero vectors, basically, right? So if I want to, so this proves that f preserves composition, but another thing f needs to preserve is the special arrows, right?
Yes.
So if I take point P, and the special arrow as a vector is just the nil vector, right? And so with the nil vector, the parallelogram rule gives me back that vector. Imagine a parallelogram where the height of this is 0.
Yeah.
And then what will be f of p?
So if we think we can maybe kind of draw in, this is a vector, but this is like a vector, because it's the same point, this is a vector that has no length.
Yeah.
0 length. And then when we do the parallelogram rule, this will also have 0 length, this one.
Yeah.
So this point will map to itself then, because this is 0 length, the t will be mapped to itself. Right?
Yes.
So f of the, f of the identity arrow of p will map t always to itself. And that's the other rule that the functor needs to satisfy.
Yes, that makes sense. Geometrically.
And now it's so we've kind of we've done something very interesting, because we didn't really do any like elaborate calculations to make sure everything works, but on the side of intuition and geometry, we kind of achieved that. And so it's a nice example of how this story in a mathematics can always split up. You work out something on the intuitive side, you're happy with it, you feel that it works, but you want to be really super sure, and then you have to do the algebraic calculations to confirm that, which is of course something that will be left for whoever is watching this video. So one would have to then take all these definitions and formulas and confirm, firstly, that all these vector spaces we ended up with were actually vector spaces. So this way of defining 0, plus, and scalar multiplication satisfy all the vector space axioms. And then also to confirm, not using geometry, but using the formulas we gave, that this capital F is a functor.
Yes.
So you would end up with like long calculations, but every time you feel like you're lost with those calculations, you go back to the pictures and you get back on the intuitive track by comparing it with the corresponding picture.
Yeah.
Great. So do you think? Yeah. So the only other ingredient of this slide is this idea of HOM. But this notation of HOM A isn't really used that way in category theory. What HOM usually represents is, HOM is usually applied to two objects rather than just one. And HOM of two objects represents the set of arrows from A to B. But with HOM only acting on one object on the picture here, it kind of means that we are collecting all the HOMs for all the B's, and it's kind of intuitively saying that we are viewing these points as vectors that connect them with the chosen origin.
Oh, okay.
So this picture is supposed to say that this point gets mapped to a vector space where this point is seen as the origin.
Okay. Yes. Everything makes more sense now.
Mm-hmm. The other thing to remark here is that we're not really capturing coordinate transformations with this because we don't really care about coordinate system. We only care about the origin of the coordinate system in this story.
But wouldn't changing the origin then cause a coordinate transformation? Because when we look at our addition...
Yes, but usually when one talks about coordinate transformation, it's not only about changing the origin, it's also about changing the axis.
But wouldn't the axis essentially change?
We have never fixed axis in this story. The axis would change, but we have never specified exactly what the axes were in the beginning and how they will change. Because all of this we could describe without knowing what the axes are. So all of this is invariant under specification of axes.
Oh, okay, I see.
But in physics, when one talks about coordinate transformation, one has in mind not only change of the origin, but also change of the actual coordinates. Now, Professor Honerkamp could correct me here, but as far as I can tell, this story only tells the story of coordinate transformation as much as changing the origin is concerned. And if coordinate transformation in physics does mean also working with the axis, which I think it does, then that story is not captured here. But the answer of Dr. Partha Ghosh about coordinate transformations with the matrix representation of linear maps and the functor we described there at the lecture, that was actually the correct answer in terms of how to view coordinate transformations from the point of view of category theory. But of course, it does require a lot of elaboration and going in detail on that side as well. Okay, do you think we can end here? Do you think we've kind of at least given an idea how to solve this exercise?
Yes.
Yes, I think so.
Definitely.
Fantastic.
Now it's just only verification in terms of to make sure that everything that we said is what we said it is.
Exactly, yes. Yeah,
what we speculated it is.
Kind of almost like the boring part remains now to carry out the calculations, right?
Yes.
It's the proofs.
Mm-hmm. Yeah. Okay, thank you so much. I'm going to now stop this recording. So I just wanted to add one last point, or maybe not last, but at least for now. Something I realized as I was preparing to upload this material. This picture that we drew of these two parallelograms giving us the third parallelogram demonstrating functoriality of the construction we gave in the video. The picture wasn't very good in the sense that it was a bit too restrictive because we kind of drew these arrows to be collinear, and they don't have to be collinear. So a better picture would be the following. It would still give the same result, as we will see, but it is more representative of all sorts of scenarios that can happen. So let's say P and Q are arranged like this, and then for the point R, It could be somewhere else, not on the same line as P and Q lie. And then performing the first, so let's say then the other point that represents T is somewhere there. So performing the first mapping would give us this parallelogram. And then the second mapping would give a parallelogram here. Now that has to match with the result of the mapping of the initial point T according to the PR vector, which now is this. And again, if we draw the parallelogram in, we would, of course, geometrically we see we end up exactly where we want to end up with. So the FPQ mapping will map this point there. The FQR mapping will map that point here. And if I combine these mappings, eventually this point ends up being mapped there, which is the same result as the mapping of this point by FPR, which would directly perform the mapping according to this outer parallelogram. So of course the thing that was wrong with the previous picture was that here we chose these two vectors necessarily to be on the same straight line, which lost the three-dimensional nature of this picture. Well, actually not really three-dimensional in the sense that everything is happening on the plane because we chose our space to be r squared, but still the picture is a bit less trivial than what we made it to be by choosing those vectors to be collinear. Okay, so that's one thing I wanted to add, and the other thing I wanted to add also, it's a discussion that we had with Luke and Summayah after we stopped the recording. There was a question that was asked, which I think is a very important question, so I want to include this in the video as well. There was kind of feeling that maybe this whole story is just about different ways of representing the same thing, but actually it isn't. So what I mean here is that the way these vector spaces are defined, the way we define them is not just different ways of representing things. The structure of those vector spaces are genuinely different from each other. For example, in the vector space where origin is xy, let's say, the sum of these two yellow points would be given by that yellow point. But in the vector space where the origin is, let's say, 0, 0, so that would be a vector space with that would correspond to it will be the vector space f of the point 0, 0. So in that vector space, the sum of these 2 points would be something that results from the corresponding parallelogram, which is of course a different parallelogram than the other one. So the sum of those points will be that one. So in general, to add points, we need a reference point as well that determines how to add them. Otherwise, we can't add them. And by choosing different reference points, then the way we add them becomes different. And so that's the essential difference between these things as vector spaces, although they all have the same underlying set, which is r squared. Okay, so these are the two things that I wanted to add to this video.